Chapter 4 is titled Quadratic Functions and Factoring. You'll notice there are 10 lessons in this chapter. We're going to start with graphing quadratic functions in standard form. Our goals today are to identify key features and graph in standard form. So far, everything we've graphed and worked with has been in the category of linear functions. We've had slope-intercept form, we've had direct variation, we've had inequalities, and then we've had absolute value, which is kind of a broken up linear function. In each of these equations, x has an exponent of 1. In this chapter, we'll explore a new type of function. Over on the left, quadratic Paren function is now defined as y equals a times x squared. So you'll notice we're raising the exponent up to 2. For the Paren function, the a value will always equal 1. Over on the right, you see the graph of that quadratic function. It has a curve that kind of goes down and then comes back up. The vertex or turning point is very similar to absolute value graphs. The vertex for the Paren function is right at the center at 0, 0. Now what we didn't plot with absolute value is the axis of symmetry. The axis of symmetry is going to be the equation of a line that goes right through the center. And it's always going to be a vertical line. And what we do is we kind of draw it in with a dashed segment. It splits up the left side and the right side. If we were to fold the graph over on that dotted line, the curve would match up from one side to the other. One other key feature would be the y-intercept of this graph. Notice it's also at 0, 0. To get the shape of the curve, we would actually make a table. So I have a table drawn over at the right. We'd pick values for x and plug it back into the equation. If we start with 0, into the equation y equals x squared because a equals 1. 0 squared is 0. And notice that point is plotted on our graph for us. If I count 1 to the right, that'd be positive 1 on the x-axis. And if I square that, 1 squared is 1. And you see that point plotted. Watch how fast this graph will grow. If I plug in 2, the next value on the right, 2 squared goes all the way up to 4. And if I would have plugged in 3, that'd go off our graph already. 3 squared would be 9. So you'll notice it's not a straight line that connects those points. And if we go in the other direction, we see some symmetry. Negative 1 squared would actually still be positive 1, and you see that reflection. Negative 2 squared would go up to positive 4. So again, if we folded that graph over, it would map onto itself. This again is known as the Paren function. From here, we can actually change the location of the vertex. We can make the quadratic function open up or down. We can make it stretch or compress. And if this all sounds familiar, this is essentially performing a transformation of the Paren function. Now the shape that the quadratic function forms is called a parabola. So if I ever say parabola, that's just the shape of the quadratic function. All right, let's go ahead and start changing things up. Now let's focus on what the a value can do to the shape of the graph. If the a value itself is greater than 1, we describe the graph as stretches vertically. That U shape or that parabola will become more narrow looking because the y values get so much bigger even faster than they already did. I'd like you to add in that second kind of comparison, the 0 is less than the best you can in your note packet. If you need to rewrite it, go ahead and do so. This means if the absolute value of a is between 0 and 1, which means it would be a fraction, it's going to compress vertically, which means it'll draw all your y values closer to the x-axis, and it'll make that parabola look wider than the Paren function. And then last but not least, if a is a negative value, Just like absolute value, it will make it reflect over the x-axis. So let's put those descriptions to the test. Describe the transformation, then sketch the graph. F of x equals negative 4x squared. So notice from the parent function, we have an a value of negative 4. When it was an a value for absolute value, we're going to describe the transformations the exact same way. The negative means this quadratic function will reflect over the x-axis. And since the absolute value would be 4 and that's greater than 1, this graph is going to stretch vertically. To draw or to create the shape of the parabola from the parent function, we're just going to create a table. We'll pick x values and then plug it in to figure out our y values. If we pick numbers similar to the x values up above, I'll start with 0. Plugging in 0 for x and squaring it would stay 0, times negative 4 also stays 0. So notice the vertex didn't change. But if I plug in 1 for x, 1 squared is 1, times negative 4, now I go all the way down to negative 4. So over 1 to the right, and I'm already off the graph. If I were to count to 2, 2 squared is 4 times negative 4, that would go all the way down to negative 16. And that's too far off of our graph even to plot. So I'm going to go to the other side and go to negative 1. Negative 1 squared would be positive 1 times negative 4. There's our symmetry, negative 1, negative 4. And well, that's down a little bit lower, so we'll put that one up a little bit so that matches. And if I went to negative 2, that would go down to negative 16. So already way too far off of our graph. As we look at the dots over here on the right, I'm just going to clear that up a little bit. Notice our vertex is at the same location, but our dots that have symmetry are upside down. As I connect them, I'm going to have kind of a curve that goes up and then comes right back down with arrows on both sides. Technically, our parent function should have arrows as well, so maybe we should include those in there. So notice our graph reflected over the x-axis, and it stretches vertically. It's more narrow looking than the parent function. Let's try the next one. G of x is equal to 1/3 x squared. Now our a value has changed to 1/3. Since 1/3 is between 0 and 1, this graph compresses vertically. And notice it's positive, so it'll go in the same direction as our original graph. All right, on the parent function, I'm just going to draw some arrows in there quick. Now let's go ahead and create a table for our new graph. If I plug in 0 again, we're going to square that first, order of operations. 0 squared is 0, times 1/3 stays 0. So far, our turning point or our vertex stays at the same location. But watch what happens if I go 1 to the right. 1 squared is 1, times 1/3, we're just going to go up a little teeny tiny bit. 1 to the right, up 1/3. If I go 2, 2 squared is 4, times 1/3 would be 4/3, or 1 1/3. So not that much bigger either. Look at that. Get that dot in there, try to make that a little bit bigger. There we go. I'm going to go 1 more to the right and see what happens. If I go over to 3, 3 squared is 9. 9 times 1/3 would be 3. So that's a nice ordered pair set to plot. So you can kind of see how your outputs are getting bigger than they were for the parent function. And if we go in the other direction, negative 1 squared would be 1 times 1/3. We're going to get that symmetry again. So over to the left, up 1/3. If I go to negative 2 squared would still be positive 4, times 1/3 would be 4/3. So negative 2 up 1 1/3 or 4/3. Negative 3 would put us at positive 3. So negative 3 up 3. you can kind of see the shape of that parabola getting wider, or the y value is actually being pulled down or compressed towards the x-axis. I'm just going to draw a curve through those points on the right, try to get through as many as I can here. Arrows up all the way to the top, and do the same thing over here on the left. When you flip it over, we'll take a look at moving the vertex as well. Oh, look at this. Anybody who knows me knows we're going to have some steps at some point, right? Now, standard form for a quadratic function that has a transformation of the vertex as well is f of x equals a times x squared. And now look what's happening. We have plus bx plus c, where a, b, and c, they're just numbers. But when you have that x squared term and an x term, we know we're going to have a vertex that's been moved from 0, 0. There are 4 things you're going to want to determine when we're in this standard form. The first thing you want to calculate is the new vertex. You need an x and a y. So the first thing you'll do is you'll use your coefficients a, b, and c for help. The x-coordinate of the vertex is found by the formula negative b over 2a. Always simplify that fraction. If you have 2 negatives, the fraction becomes positive, and if you can reduce the top to bottom, always do that first. Then the second thing you want to do is get your y value by plugging x back into the equation. So this is the step where you do the most amount of work. Make sure your vertex calculations are clear. Okay, from there, you get that axis of symmetry. So we're actually going to draw in that axis of symmetry. And the nice thing is it's x equals a number. So it'll be like x equals 2 or x equals negative 1. And the number you get is the same as the x value of the vertex. There's no calculating here. You just identify that equation and then you draw that vertical dashed line in. Step 3, finding the y-intercept. This doesn't involve any work either. The y-intercept is always going to be the constant at the end of the equation that doesn't have an x with it. The other two, if you plugged in 0 for x, would just cancel out anyway. And then what you do with the y-intercept in the axis of symmetry is you create a reflection point. You're going to reflect the y-intercept over the axis of symmetry and plot that on the other side. That should give you enough information to sketch the parabola through the points. Let's give it a shot. List the key features of each quadratic function, then sketch the graph. Example A, y equals 2x squared minus 8x plus 6. We know this is going to be a transformation of the parent function where we move the vertex. That means the first thing we need to do is calculate where the new vertex goes. So I'm going to put my answer here when I'm done. To get the x-coordinate, we use the formula negative b over 2 times a. b is negative 8. So I'm going to substitute that in the numerator. A is 2, so 2 times a will be 2 times 2. We have that double negative, which will actually cancel out, and that gives us 8. Over 2 times 2, which is 4, and that reduces to just positive 2. That's the x-coordinate of the vertex. You're going to want to take your time on that. To get the y value, we plug x back into the equation. We'll have 2 times x squared, which will be 2 squared, minus 8 times 2 plus 6. And now we have to simplify. Order of operations, we're going to do 2 squared first and get 4. 4 times 2 is 8, minus 8 times 2 is 16, plus our constant, which is 6. 8 minus 16 plus 6 gives us a y value of negative 2. Let's write our answer as an ordered pair. 2, comma, negative 2. That's the most amount of work. Everything else we're going to get either from the equation or from our answer in the vertex. 2, our axis of symmetry. I'm going to pick a different color so when I draw it in, it's just more kind of visual. So our axis of symmetry is just the equation of that vertical line. So it has to be x equals And we use the same value as the x-coordinate of our vertex. So it's going to be at x equals 2. And that's it. That's all you do for that step. The y-intercept, remember we said it's just the value of the constant in the equation. If we plugged in 0 for x, everything else would cancel. The constant is 6. Therefore, our y-intercept is 0, 6. That's it. To get our reflection point, what we're going to do first is graph the first 3 steps. All right, so I'm just going to identify what we're going to do here. So now let's go ahead and plot the given information that we have so far. Our vertex is positive 2, negative 2, so down here on the bottom right. Our axis of symmetry, remember, is that dashed vertical line. We're just going to draw that in all the way through. I kind of run out of space down here, so you're going to want to draw that all the way to your edge. I'll have to scroll my screen up for the next one. And then our y-intercept is 0, positive 6, so way up here. What we mean for reflecting is notice how far away that y-intercept is from the axis of symmetry. It's 2 units away. So if I reflect it, it's going to go 2 units even further on the other side over here to the right. So I'm just reflecting it, counting over how close it is to the axis of symmetry, and then reflecting it to the other side. Now that ordered pair is all the way at 4, 6. So I'm going to identify that reflection point. Notice the vertex is down below at 2, negative 2. So if I sketch a curve through these 3 points, I'm going to create the parabola. It goes down and then comes back up on the other side. Arrows at the top. And there's your quadratic function in standard form. Let's try to get one more in here. F of x equals negative x squared minus 2x plus 1. We know this is going to be a transformation, so the first thing we're going to do is calculate the vertex. With the negatives and the x squared and the 2, we need to make sure we're super careful on this one. We'll start with the x-coordinate. X equals negative b over 2a. If it's negative b and b equals negative 2 over 2 times a, and a is negative 1, the negatives will cancel out in the numerator, giving us positive 2, but in the denominator, 2 times negative 1 is negative 2. That will simplify our x-coordinate to negative 1. And we have to plug that back in. Oh, goodness. Here we go. Y equals. Well, that should be an equal sign. Let's make that count. There we go. Try that again. We have negative x squared. So we're going to do negative 1 squared. We have to think order of operations on that. Minus 2 times negative 1 plus 1. Order of operations, negative 1 squared is 1, but the negative on the outside changes it to negative 1. Minus 2 times negative 1, which is negative 2, plus 1. When 2 negatives are side by side, they're going to cancel out to be plus. Therefore, negative 1 plus 2 plus 1 puts us up at positive 2. That means our vertex is negative 1, 2. If you can work your way through that, remember the rest of your points are free points, so take them. Step 2, get that axis of symmetry. I'm going to change my colors again. Remember, for full credit, it must be written as an equation, x equals. And it's always the same answer as x in the vertex. There you go, done. Step 3, y-intercept. That's just the same as the constant in the equation, which is positive 1. Let's go ahead and plot these 3 things. Our vertex is negative 1 up 2. Our axis of symmetry is x equals negative 1, so it's that dashed line all the way through at negative 1. Arrows at the top and bottom. And our y-intercept is 0, 1, over here on the right. To get step 4, our reflection point, we're only 1 unit away. So if I just reflect over that axis of symmetry, I end up going to the left this time. And my reflection point is at negative 2, 1. Well, notice those dots are kind of clustered together. They're pretty close. So what I would recommend doing is creating a table to figure out a couple more points to get the curve for that parabola. Whatever we pick for x, we have to plug in for x squared and negative 2x up above. Well, I already have 0, so I'm going to count 1 to the right and plug that in for x squared and 2 times x. If I plug in positive 1 and square that, it would be 1, but times that negative would be negative 1. Minus 2 times 1, which would be 2, plus 1, that actually puts us at negative 2. So I'm going to plot 1, go down to negative 2, and I'm going to reflect that point to the other side. It was 2 away, so I'm just going to reflect it over to the left. There we go. I'm going to pick one more number, positive 2. If you plug in positive 2 to your equation, you'd actually get negative 7. So I'll count over 2 to the right, down to negative 7. Now, if we reflect negative 7, it's 3 units away. And if I go 3 units to the other side, it now appears we have a decent amount of points to connect and form our parabola. Notice this graph opens down, so it reflects over the x-axis. We have our vertex, our axis of symmetry, and our y-intercept. I think that's enough for this video. We'll go ahead and complete the rest of these notes in class tomorrow.